Okay, so today we will continue to talk about medium access control and finish off the part about random access, or what should we call it, uncoordinated access, and then go into the more structured schemes and talk about channelization and so forth. So let's get started. The basic idea behind medium access control is to share a common medium. Okay, that's why we have medium access control. So a picture to illustrate what's going on here is that we have a number of stations. You can think of these as being transmitters or nodes or computers which are attached to a common medium. We can think of this as a cable, but it could also be a radio channel. These stations are generating traffic that is supposed to go over this shared medium. And the different stations could have different traffic demands. So we have lambda 1, lambda 2, and so forth, up to lambda n, where n is the number of stations which are attached to the medium. And the total data rate, which is offered to the medium, is the sum of these. Or the lambdas here can be counted in different units, depending on what is convenient. It could be like a frame per second, or even bits per second, but frames per second is normal, or even more normal perhaps is frame per frame duration. So frame per frame duration, is basically what it is, right? It's how many frames you generate per time unit, where the time unit is the frame duration. There are two, a metric which is of interest is the time it takes for a frame to be available for transmission at one station until it's delivered at some other at the other station here, and that is what we call the frame transfer time. And if we look into the station here, it essentially consists of then this medium access control that we're talking about, that layer, which is directly on top of the physical layer. So above the MAC layer, there is the data link control layers and network layers and whatnot, right? But now when we're talking about frame transfer delay here, is from when it goes into the MAC at the sending station and goes out from the MAC at the receiving station. All right, frame duration, TF, frame duration, NF, medium data rate is the ratio between these two things. It has been that for some time, but I'll just repeat that here. The offered data rate from all the users is lambda. That's the number of frames per second in this case. And then we multiply with the number of bits per frame, and then we get something in bit per second. The data rate which is offered here can only be carried by the medium if lambda times NF is less than R. Okay, otherwise this will be impossible. So the offered load is the ratio between what data we would like to transmit, that is lambda times NF divided by R, and R is the capacity of the medium. The throughput is the data rate that we actually get through here. So it's the serviced data rate from all users, and let's call that R effective here. This is similar to the data rate that we talked about when discussing retransmission protocols. So this is the data rate that the layer above the MAC layer experiences. Okay. The maximum load supported by this MAC, or the maximum MAC efficiency, is the highest load that we can support. And that's different from different setups and different protocols. So it's the ratio between the effective data rate when we maximize that over all possible parameters and divide by R. It turns out that our efficiency that we can achieve is strongly dependent on the propagation delay from one end to the other end of the medium. The longer this delay is, the harder it is to coordinate transmissions on this medium. Okay, so what is the time from end to end here? Well, it has to do with the distance, obviously, and then also on the propagation speed on the medium. So the propagation delay from one end to the other is the distance divided by the propagation speed. And this propagation speed could be quite high. It could be close to the speed of light, but it can still, anyways, be a significant delay that makes it complicated to coordinate this axis. As a matter of fact, it becomes complicated, or more challenging to coordinate this when the normalized delay bandwidth product, which is the ratio between the propagation delay and the frame duration, when this starts to become large. Okay, then we have problems or more challenges in coordinating transmissions here. All right. We talked then about, so this was in general. So the question is, what kind of MAC protocols can we have here? Well, the simplest one is called ALOA. And basically what it does is that when a station gets a frame from the layer above it, it just simply transmits it regardless. Okay, and then collisions are detected by seeing whether we get an acknowledgement or not. If we don't get an acknowledgement before a timeout, then we back off. That is, wait a random time, and then we try again. So that's ALOA. It's the simplest thing we can imagine. But it's not, I mean, it's beautiful in its simplicity, so it's actually used in practice also. But it's not super efficient, as we will see. So the normalized throughput we can get for ALOA and other schemes is the average number of successfully transmitted frames divided by the frame duration. So if we count the number of successful frames during a certain time, and then we divide through by the frame, the average number of successful frames, that's the number of successful frames per, okay. Okay, let's try again. The average number of successful frames divided by the frame duration. Then we get a number which is called S. It's also the average number of transmitted frames divided by the frame duration, and then multiply with the probability of success for that frame transmission. Because remember now that when we transmit over this medium, bad things could happen with this frame. It can be lost. And now we're only concerned about losses which are due to poor coordination of the medium. And poor coordination of the medium, it happens when there are collisions on the medium. And then we say that that will be fatal for all the frames which are involved in the collision. Then there could also be errors due to noise and so forth, but we will ignore that in our study of the MAC layer. That was very important for the physical layer, but let's assume that the physical layer is either very good or we just simply ignore those type of problems. Then with probability of success here, what we mean basically that success is equal to no collision on the medium. Okay, so for ALOA we did a very simplified analysis of this, and it turned out that S is G times e to the power of negative 2G when it's unslotted, and when it's slotted the only difference is that there is a factor 2 that disappears in the exponent here. And if one maximizes this over G, then we get the maximum throughput, normalized throughput we can get, which is 1 over 2E. E is the natural Euler's number, the natural number. And G here, what is that? Well, it's the average number of frame transmissions per frame duration, including then retransmissions. So there are some new frames coming in to be transmitted, and at the same time there are some retransmission frames coming in, and both of these contribute to G, but only S of those gets out of the system with our successful transmissions. All right, so ALOA, there are two variations of it, unslotted and slotted, with different performance. Can we do better than this? Yes, we can. And then we use something called carrier sense multiple access. And the improvement on ALOA is basically that we listen or sense the channel for ongoing activity before transmission. So we sense the channel, so if it's idle, then we transmit. If it's not idle, then we do something else. Typically wait for a while and try again. And we will talk more about different alternatives for what to do when busy. But the improvement here is kind of obvious, right? Since we say that collision will be fatal for all the frames which are involved in the collision, then if we are ready to transmit and we sense that there's a transmission ongoing, then if we transmit, not only will we sabotage the ongoing transmission, our frame will not get through either. So there is simply no reason for transmitting if we know that there is an ongoing transmission. All right. So then there are different, okay, so this is the general idea for carrier sense multiple access, or CSMA. So let's discuss what to do when the medium is perceived as busy, because here there are different alternatives what we can do. There is something called, and this is called different types of persistency. So there is one persistent, non-persistent, and p-persistent. So let's skip this slide and go into some pictures to show what's going on. P-persistent is the most aggressive version. So what it does is that if a station has a frame to transmit, it monitors the channel until it becomes idle and then transmit. Okay. So here, sense idle channel. So this happens, you know, a picosecond before transmission. Okay, so the time when we declare the channel as being free, we simply transmit. Okay, so this is an aggressive version of it. A non-aggressive version is this non-persistent one. So what do we do then? Well, we sense the channel, and if it turns out to be busy, then we back off for a random time. Then if we sense the channel to be busy again, then we back off for a random time. And then when we sense the channel and we sense the channel to be idle after the back off time has expired, then we transmit. Okay. So this is a little bit of a more polite way of accessing the channel, because different nodes. Okay, so what is the problem of being aggressive here? Any suggestions? Yes?
Collisions, perhaps?
Yeah, exactly. So suppose then there are two nodes who are starting to sense the channel during the same transmission here. Then they will both sense the channel to be idle at this point in time, and then they will hit the channel and their frame will collide. Okay. So as soon as we have more than one node becoming ready meaning that it has a frame to transmit during this busy time, then for sure there will be a collision here. That is sort of mitigated here, because here each node will have a backoff, and the backoff is random, so it's randomized between different nodes. It can be short, it can be long. And with this randomization, if the range of possible backoff values is large enough, then the probability for a collision is relatively small. Okay. But what is the drawback of the non-aggressive version here? A lot of waiting time, right? Exactly. It could be like if this happens to be the only node which is waiting for the channel, then the channel will be unused during this time for no reason, right? So there is a trade-off between the delay a node experiences and possibly also the idle time on the channel with the probability of collision. So here, very little delay, but high probability of collision, relatively high probability of collision. Here, long delays, but relatively small probability of collision. So there is pros and cons with both of these, right? So one has to, by designing parameters here, one can sort of optimize depending on how the situation is. And what I mean by the situation, I mean the number of nodes which are attached to the medium, a little bit by frame lengths, delays, and so forth. So one can optimize this. Okay, and one way to optimize this is to use something called p-persistent, which is a hybrid between these two things. And it works something like this, that when a station becomes ready, okay, meaning that it gets a frame from a higher layer, it starts to sense the channel. And if the channel is busy, then it continues to sense the channel until it becomes idle. When it comes idle, it doesn't transmit, but basically monitors it transmits with a probability p. Okay, so this cryptic thing, send here when r is less than p, that will be clear on the next slide. But what it basically means here, that at this point in time, we transmit with the probability p. So random event here determines whether we transmit or not. So say p is a half. Then with the probability 1/2, we transmit at this point. With the probability 1/2, we don't. And if we don't, we wait for a time slot. And as long as this slot is idle during this time, then we will try again. If the channel becomes busy during a time slot, then we back off. And after the back off, if we sense the channel, either it's busy and then we go into back off again, or if it's idle, then we transmit, but only with probability p. Okay, so we transmit here with probability p. And suppose we don't transmit here, then we wait another time slot during which the channel needs to be idle, otherwise we go into back off. And then we repeat our experiment, and with probability p we transmit here. So after some time, we will transmit. Okay, but it's not clear when. It was sort of like a random time before we transmit. So any questions on this? We can look at some state diagrams also to see whether we can make further sense out of this. So this is the state diagram of this, and here's p persistent. So we enter in here when station becomes ready. Has a frame to transmit. Okay. So once we get a frame from the layer above, we go down here, and in p persistent, we sense the channel. Is the channel busy? Yes. Then we go back, sense the channel. Is the channel busy? And then we roll around here until the channel becomes idle, and then we transmit. Okay. So that's the aggressive version, the one persistent one. The non-persistent here goes into this, and if the channel is measured the channel, if it's busy, then we wait randomly, and then we go back and measure the channel. Is it busy? Then we wait randomly. So this wait randomly is the same thing as going into back off. Okay. Now, if on the initial axis or the initial time whenever the channel is declared to be idle, that is not busy, then we transmit. Okay. Here is the p persistent one, which is a little bit more complicated, but let's go through it. So we go into this, and then we look at, is the channel busy? Yeah. Then we go around. So this is just as one persistent. This loop is the same loop as here. And then once the channel becomes idle, instead of transmitting immediately, we generate a random number from 0 to 1 and compare that random number with p. If the random number is less than p, then we transmit. Okay, and this happens with probability that R is less than P, which is P. P is fixed number. Okay, P is a parameter in this. So R is the random thing here. R random. Okay, so for each time we generate a new random number when we go down here, and then we compare it to P, and either we transmit or we don't. If we don't, then we wait a slot and then measure, is the channel busy? If it's true, then we go into back off, and then we jump up here again. If it's not busy, then we go up and generate a new random number, compare that with P and transmit, or we don't transmit, and then we go back like this. So eventually P persistent will eventually transmit. It's unclear when, but eventually it will be. And why this is called 1 persistent is because it's P persistent when P is equal to 1. That is, we always transmit. I mean, otherwise, if we go down here and P is equal to 1, we will always transmit. Okay. All right, any questions on these persistence methods? No? Okay, so let's continue then. So another variation of CSMA is called CSMA with collision detection. So remember again, so what do we do when we do carrier sense multiple access? Well, we measure the channel, and if there is no activity on the channel, we declare that to be idle, and then we can possibly transmit. However, due to the delays of the medium, it's not 100% sure that the channel is not used just because we cannot measure any activity on it. And this has to do with the fact that there are delays. So it could very well be like if we have, this is the medium, and we have station 1 here. It can start to transmit the frame at some point in time, while that frame, if it hasn't reached station N here, for instance, then station N will measure the channel and say, hey, it's idle. Although there is a frame already on the medium and it's going in the direction of station N. Okay. So sensing the channel and not sensing any activity is not the same as saying that the channel is not used. The channel could be used, but sensed as being idle. Okay. Okay. So how do we detect that there are collisions? Well, basically we use the same method as in ALOA. That is, we transmit a frame, and if we don't get an acknowledgement, then we assume that there has been a collision, and then we retransmit somehow, according to some method. Okay, so collisions are normally detected by the absence of an ACK. That is, when the timeout expires, if we haven't gotten an ACK, then we assume that there's been a collision, and then we have to recover from this, typically by retransmission. However, if one can sense the medium while transmitting, then we can detect collisions in progress, right? Because if we detect by not seeing an ACK, this is like after the collision has occurred, at some point later in time, we will not get the ACK, and then we declare that the collision has occurred. But if we can measure the channel while transmitting, then we can detect collisions when they actually happen. Okay. And this is good because then we can quickly recover quickly from this collision than in the former case. Okay. So colliding frames again are typically lost, And while if we then detect a collision in progress, there is no need to keep on transmitting the frame because it will anyways be lost. So we just abort that frame transmission and try again. Okay, so this is known as CSMA with collision detection. So what it does, basically, we sense the channel just as we do in CSMA. If busy, then we have some persistence method, persistent, non-persistent, or p-persistent. If it's idle, okay, then we can transmit. Then we transmit, and at the same time, we listen to the channel. And if a collision is detected during transmission, essentially is like what we transmit is not what we hear. We hear as some other frame also. During transmission. Then we stop transmission after a short delay, and then we back off a random time, and then we sense the channel again. These 2 points here, it's easier to show on the next slide what's going on here. So here's an example of this. We have 3 stations, A, B, and C, and A senses the channel. Okay, we have an idle channel here. Okay, which means that we transmit. Okay. This green frame then reaches node B here and node C here. What happens is just there is a period which we call the vulnerable period. It's the period when C does not detect the transmission, a start of a transmission of a new frame. Okay, so this is known as the vulnerable period. It's the time when sensing does not prevent a collision, or rather, when sensing does not detect an ongoing transmission. And this is equal to the propagation delay, right? So it takes t-prop seconds to go over the channel. So during this time, the vulnerable period, C might have a frame to transmit, and suppose it arrives just a tiny little bit of time before the frame from A arrives, then C can also declare the channel as being idle and transmit. And then we have a collision, okay? So during this time, the frame from C goes over the channel. It will collide at B here, and it will also arrive at A 1 t-prop second after it started to be transmitted. So we will have a period here which is equal to 2 t-prop when several nodes can try to access the channel even though they use carrier sensing. But after 2 t-prop seconds, so when A has started to transmit its frame, after 2 t-prop seconds, A would know that there has been a collision or there has been no collision, if it can do sense the channel at the same time as it transmits. Because if there is no other frame that has arrived after 2 t-prop seconds, then station A knows, okay, I own the channel. I'm the only person on the channel, so now things are good. However, if another frame arrives during after a delay which is less or equal to 2 t-prop seconds, then we know a collision has occurred, and then there is no need to keep on transmitting, right? Because we know there will be a collision, and probably my frame will be lost, and also the other nodes. So what happens then is that station A detects the transmission from station C at this point, and then after a very short delay, it stops transmitting here. Okay, so this is the green thing here is not a complete frame; it's just a partial frame. Okay. And the same thing C here, when it starts to transmit, it also notices that there comes a frame here from A, and it says, oh boy, there is a collision. So after a short while, it stops to transmit also. And then at this point in time, one just simply waits and try again. So here, this contention period is when several stations are competing for the channel, and one of them will either win, or there will be a collision, and then both has to retry, typically after a back-off. Okay. So this works, and it only works if the frame length that we transmit is at least 2 t-prop seconds, because if it's not, then we will not detect that there is a collision, because we have stopped transmitting before the other frame arrives. Okay, so the minimum frame length here needs to be greater than 2 t-prop. Then if no collision is detected during the contention period, then we know for sure that the node is then sure that it successfully captured the channel or won the channel. Okay, because then after that, all other nodes on the medium will, when they do sensing, will hear the green, the frame. Okay, any questions on this? Okay, so the basic, the good thing about collision detection here is that we can detect collisions quickly, and we can also stop transmitting because there is no need to transmit when a collision has occurred. Okay, so these are the two good things about this. So, yes?
Why doesn't the C stop transmitting directly? Why does it have to wait a while?
Okay, so that's a very good question. So why does C continue to transmit during a short period here? And the reason for this is that it needs to inform the other side that there is a collision. And the only way to one way to do that is to transmit for a tiny period of time, such that A has a reasonable chance to detect this other frame. Okay. Yeah. Okay. That's a good question. So here's a flow diagram of this, and this is in particular also with the back-off period here, where we use this binary exponential back-off procedure. That is, the back-off time is likely to be longer for each time we go into back-off, consecutive back-offs. So let's go through this. So we have a station, it becomes ready, it has a frame to transmit, and then K, which is the number of times we have retransmitted this frame, is equal to 0. And then we go in and we use some persistence method, and then we go into carrier sensing. Or rather, here we start to transmit. So transmission starts here, and during transmission we sense the channel here, and if we are done or if there is a collision detected here, we go out of the loop, and if there is a collision, then if there is not a collision, then everything has gone well, and then we're successful. If there has been a collision, then we transmit this short signal, just to make sure that the other side hears that there is a collision. And then we increment K, and then if K is less than K max, then we go into back off. If K is equal to K max, then we abort, we give up. But if K is less than K max, then we generate the random number, and that random number is a number between 0 to 2 to the power of K minus 1. So we see when K increases, the range of possible R's increases also. And then we take a random number, and then the back-off time will be this random number times the frame duration. Okay. And then we wait for this back-off time, and then we go in and we try again. So each time we go around this loop for the same frame, we increase the maximum number R can take on, which means that we increase the maximum number TB can take on. But at each time we run through this, we pick a new random backoff. So the backoff could be, bigger, smaller, but it tends to become bigger as we go around in this loop, simply because we have more large numbers to choose from or randomize over. Okay, so this is a binary exponential backoff. Questions on this? Okay. So the reason why we increase this back-off duration, why is this? Why do we increase the possible values of R as we go around here, you think?
Perhaps the channel is where we set the moment.
The thing is the following, is that when we have a collision, we don't know how many nodes are involved in this collision. Is it 1 node, 2 nodes, 5 nodes, or 200 nodes? We don't know. We just detected a collision. And all of those nodes who have detected a collision go into backoff. And what we want to do is to have randomized backoff such that the probability of another collision next time is as small as possible. Okay? But on the other hand, we don't want the backoff to be very large unnecessarily. So we start with the short backoff window. And if that didn't work, then, okay, maybe we need to increase it. If that didn't work, okay, we increase it even further. So this is a way of adapting to the number of nodes which are involved in a collision, ongoing collision. And we never know how many of these could be because we don't know how many nodes have data to transmit at any given point in time. It could be just one other node or it could be 100. We don't know. Okay. So it's actually a smart way of adapting this backoff time. So is this any good? Well, if one do a simplified analysis of this, we see that rho max is, well, it's the effective data rate divided by R. R is the data rate on the medium. And with some approximations, one can write it as this. Okay, so here again, our friend or our enemy, the normalized delay bandwidth product comes into play, and then this E here is the Euler's number, 2.7. What is it? 2.718 something? 2.7 anyways. So actually, this E here comes a little bit from that we approximate some things going on here with the slotted ALOA. But it's not important for this class. Anyway, so this is better than CSMA without collision detection. It's also better than ALOA, at least when A is small. Okay, when A is larger, it doesn't matter so much. So here's a figure I stole from the previous course book. It was given without much of a reference, so I have not presented the equations for these things, but what it is, it shows rho max, the maximum load we can support as a function of A. So when A is small, then we see that CSMA CD provides a good efficiency, but as A increases, we see that it drops. And we also have curves here for one persistent CSMA and non-persistent CSMA, which is a little bit less performing than when we have collision detection. Anyways, at some point we see that most of these schemes basically are equally good as slotted ALOA, or even more interesting, after a time, they're equally good as ALOA. And if something is equally good as ALOA, what should we choose then? ALOA or something else? ALOA, for sure. ALOA is the simplest we can do. We should never do anything more complicated than what we need to do, right? So for sure, for large normalized delay Doppler, normalized delay bandwidth products, ALOA is not a bad thing to do. But we can do better for smaller A's. Now, also this curve here, the slotted ALOA curve here, does not take into account that we also need a guard interval, which has to do with the propagation delay. And that is neglected in this curve. So probably it's very optimistic to think slotted ALOA will perform as good as it does up here. It will probably be down here somewhere. So a more, I don't know what the curve would look like, but something like this maybe. Okay. while unslotted Aloha, it doesn't care about this. Okay, one more variation of CSMA, and then we will go into the more scheduled approaches to medium access. And this is something called CSMA with collision avoidance. We had collision detection before, but we also have something called collision avoidance. So this is used in Wi-Fi, or a variation of this, and it's very similar to P-persistent. But we'll talk more about Wi-Fi a little bit later. So I will go into the details then. But essentially what we do is that we are, what we really want to do is to avoid collisions. So therefore we're a little bit, what should we say, conservative when trying to transmit. So when we detect the channel as being idle, we don't transmit directly. So it's similar to a P-persistence in that sense. But we'll talk more about that as we go along. Okay, so now remember that medium access control, there is a controlled access and random access. Okay. So we have talked about random access now for some time. This is Aloha, slotted, unslotted, CSMA, and a few other schemes here. So all of these used acknowledgements, timeouts, randomizations, and things like this in order to coordinate access to the channel. But we can also, in certain circumstances, be more structured in how we access the channel by having a schedule which is determined and so forth. It's more structured, but also more, what should we say, inflexible way of using the medium. So this is what we will talk about now. One example of a controlled access is something called reservation systems, and there are basically two versions, centralized and non-centralized. And centralized means that we have a specific node called the controller, which accepts requests to send from other stations and then issues grants to transmit. So this is similar to what should we say, how we would work in the parliament, right? You have the speaker of the house or the speaker of the parliament deciding who is allowed to talk, right, at any given point in time. And then there is a schedule, you know, first is like this party, and then there's this party, and then so forth. Okay, so we have a centralized figure, in this case the speaker of the parliament, that decides who's going to speak at what point in time. Or we have distributed systems where essentially nodes agree upon the schedule among themselves without having a hierarchy. What would be a good example of this? Well, it's basically when you're standing in line for the tram, at least in Stockholm, maybe not in Gothenburg, but in Stockholm people queue up, right? So you arrive to the station where the tram is, and then you put yourself in the line, and then you access the tram in order according to where you stand in the queue. Okay, so we will talk more about this, but let's take a 15 minutes break.